What is up, YouTube? It's your favorite math and physics tutor, Matt, Physics and Fitness, here with episode 1 of our multivariable calculus playthrough. But before we get into the fun stuff, let's check out our max squad for the week.
No.
185 by 3, decent depth and tempo. See where we're at next week. Now, if you're confused what a multivariable calculus playthrough looks like, this is the Khan Academy course, Multivariable Calculus, and we're just going to try to get through it. Nothing here in Unit 1 for me. We're going to start Unit 2, quiz number 1. Some of these early quizzes, I should know how to do them, but once we move on to the later ones, I'm going to have to start watching the videos to figure it out. My goal, throughout a couple weeks, maybe we can get through a lot of this course, maybe we can learn some multivariable calculus together. Let's get started. d2f over dy dx. I'm not quite sure, but I think you take the derivative first with respect to y, then with respect to x. You might be able to do it either way. But let's see, what would happen if we do that? We got a little tablet here. We can think about our work. First, let's take the derivative with respect to x. Obviously, the x would just go away. We get 2 ln y. Now let's take the derivative with respect to y. Derivative of ln y is 1 over y, so this would be 2 over y. We took the derivative with respect to x, then respect to y. Let's see if that's right. Now this is the first question. If we got the first one right, I'd be pretty happy. Means we might be in a good spot. Let's go. Partial derivative of f with respect to y. I think we know what to do there. Take the derivative with respect to y. Sadly, I don't know if I can click green. It's not the greatest, but we'll make it work. Take the derivative with respect to y. So how do we want to write this? I would probably keep the x minus 3 all by itself as its own term, because if it's its own term, it's not going to change too much, right? We can basically treat it as a constant. And let's multiply that by the function y squared plus 1 to the negative 1. Because now if this is a constant, we can keep that. All we have to do is take the derivative of this term. Now let's see. The negative would come to the front, and we would subtract 1 by this exponent, right? So that would be negative 2. Again, this whole time, we can just keep x minus 3 all as a constant. And let's just do one big parenthesis for the derivative of this term. So what do we get first? Negative in front of this whole thing, y squared plus 1 to the negative 2. But now we have to use the chain rule and take the derivative of the inside. What's the derivative of the inside? Just 2y, right? Nothing too crazy. So we would multiply that, because that's how we do the chain rule. So what do we got? We got a negative 2y on top, an x minus 3 on top, and a y squared plus 1 squared on the bottom. Can we find that somewhere? Looks like A. Looks like A. Let's try it. Yes! That's what I'm talking about. Cosine squared x minus x. Again, derivative with respect to y. I don't even see a y. So these are all constants. What's the derivative of a constant? 0. R sine theta, partial derivative with respect to theta. At least we have the variable we're looking for, right? At least this is a derivative. The r is a constant, so it's going to stay by itself. So all we need is the derivative of sine. Looking for r cosine theta. Derivative, double derivative with respect to y. So before we did it with respect to x, then respect to y. This one we're just going to do respect to y twice. Again, x function going to stay all by itself. I think maybe the eraser, just a big erase. That's how we do this. X always going to stay by itself. We know that. Now let's just do the double derivative with respect to this inside function. With respect to y, just 1 minus cosine y. You know that. We could multiply this x through, or, again, it's just a constant. Let's just keep it all by itself. Derivative with respect to 1, 0. And again, it's a constant multiplied by a function, right? That's why we can leave it by itself. Here we have a constant subtracted by a function. We got to take the derivative of that. So that's going to be 0. Derivative of negative cosine, positive sign, right? Derivative of cosine, negative sign. Derivative of negative cosine, positive sign. So you'd have 0 plus sine y all times x. Now we can distribute the x through. Obviously, the 0 term goes away. All we get is x sine y. Sorry about the sloppy work. Never been known to be neat. But I think we got x sine y. Let's see if that's right. Yes! Is that a perfect? And I think with that, let's check our incline dumbbell press for the week.
As soon as I saw the camera. God damn. Breathe, Matt, breathe.
60 pounds, 8 reps. Nice little pause at the end. See where we're at next week. Up next, lesson 2. Gradient, a video. Let's take the quiz. See what we got. Now, I might not know how to take the quiz. We might need a little bit of help. Looks like we even have help from finding the quiz. But let's see, can we do this one without a video? Or is this where we need to start going back? Find the gradient. Zxy minus x plus lny. Let's look at a refresher. Khan kind of guy, can you help me? Now, what do we want to do? Do we want to try the exercise? Or let's just watch the video and see if we can figure it out.
So here I'm going to talk about the gradient. And in this video, I'm only going to describe how you compute the gradient, and in the next couple ones, I'm going to give the geometric interpretation. And I hate doing this. I hate showing the computation before the geometric intuition, since usually it should go the other way around. But the gradient is one of those weird things where the way that you compute it actually seems kind of unrelated to the intuition. And you'll see that. We'll connect them in the next few videos, but to do that, we need to know what both of them actually are. So, packing together all the partial derivative information of a function. So let's just start by computing the partial derivatives of this guy. So, partial of f with respect to x is considered a constant. So x squared is also considered a constant. So this is partial derivatives in it. So the first one is the partial derivative with respect to x times sine of y. And the bottom one, partial derivative with respect to y. X squared cosine of y.
So is
and notice, maybe I should emphasize, this is actually a vector valued function. Right?
X partial,
so
the y partial,
maybe I'll give it a little bit more room here and emphasize that it's got an x and a y.
There was many boxes
we call these partial derivatives. I like to think of the gradient as the full derivative because that vectors do. But operators, what's its dimension?
I think it is. Let's take the see if we can and see if we got it. Quiz 2. So first we take the x partial, then the y partial, then the z partial, and I think we do it for the whole function. So obviously, we start with the z partial. We only have one z term. All these are going to go to 0. And, if we only have one z term, derivative with respect to z, pretty easy. This will xy. Derivative with respect to y, this one's just going to go away. We're going to get zx. This term's going to be 0, and this term's going to be plus 1 over y. So zx plus 1 over y. That seems like it's the y partial. Now for the x partial, this one is going to be zy minus 1. Remember, whenever we have a function separated by plus and minus signs, we treat them kind of separately as their own functions. And, we derive them one step at a time, one function at a time, separated by plus and minus signs. It's the multiplication and division when they're together that really combine the functions. These are just kind of, they're much more separated. And then plus, derivative with respect to x, that's just 0. Okay, is this right? Let's check it. I think we got this one, guys. I'm starting to notice I didn't watch that far in the video. Define f(x,y) equals x squared y. Let a vector equal 3, negative 1, and v vector equal 1, negative 3. We're going to have to go back to the video. Went a little bit too fast, it looks like. Gradient, gradient in graphs, gradient in contour maps, directional derivative. I think that might be what we need. Finding directional derivatives. Finding gradient, visualizing gradient, finding directional derivatives. Let's do some practice. Visual gradient. Here's a graph of the scalar, a common interpretation of the gradient. involves drawing it in 3D. What is the negative gradient? So the negative gradient's probably either going to be falling down into the slope or going up into the slope. When is the directional derivative either the smallest or the biggest? I'm going to say negative maybe means going up the slope, so let's try C. Okay, let's try A. Maybe the negative means going down. Okay, let's see. Can we do this in one try? So negative means going down into the slope. This looks like it's probably going to be 0 no matter what. It looks like it's on a flat surface. Perfect. Or, on either side, everything's kind of happening symmetrically. Think about the bottom of a parabola. What is the gradient? We said that negative was going down, so positive must be going up. So probably going up to the peak of the perfect. Negative gradient. Negative gradient's going down, right? So right down this way. Again, this one, it looks like everything happening symmetrically. So when we think negative, right, we're thinking going down, but in which direction? And whenever it's pretty vague, that's usually when it bounces out to zero. So here you would say the derivative, the negative direction would be going down. If you moved a little bit farther, it would be going down faster. But right here, where everything is symmetric, the answer is probably 0. Okay, now this I think is what we needed help with. I think this is the exact question from the quiz. A 3, negative 1. I feel like these have to be values for x and y. And the f of, maybe we start here and then we use the derivative and we plug in these values for the derivative values. It's just a guess, but let's try something like that. So first, let's try to just find this value at 3, negative 1. Why not? And it's 3 squared is 9 times negative 1. We're going to start with negative 9. I don't know. God, I just don't know. And now plus h of v, limit as h goes to 0. The limit as h goes to 0 is what makes me think we're taking a directional derivative here. We know, let's put it into the delta x and the delta y. Let's put it into that little matrix he showed us earlier. df dx is just 2xy. Y stay the same, basically constant. Derivative of x squared is 2x. Derivative with respect to y is just going to be x squared. That y goes completely away. Now this is where I'm thinking we use 1, negative 3. This is where I'm thinking x is 1, y is negative 3. This one will be what? Negative 6. This one will be 1. Now I'll admit, this is where I don't know what to do. We're just going to add all the numbers together, get the wrong answer, and then see what happens. Negative 5. I mean, I want to say negative 14 if I'm just adding them all together, but I can't imagine that's the right idea. Oh my god, get help. Let's see, how do we do this? This makes sense. Okay, so you're using 3 plus h as our x term. Okay, and then they FOIL it. Our y term, instead of negative 1, is negative 1 minus 3h. Ah, plus h times this direction. I see. So this is going to be minus negative 9. So that's where I was correct, because I knew that f of a here was negative 9. And now minus, I was confused. I knew something was going to be wrong. So the minus negative 9 becomes a plus 9. That should not be too surprising. Here, they use our value plus h of this direction vector v. H is going to 0. That becomes, here we're moving, in 1, h goes to 0, direction of the x direction, and minus 3 h goes to 0 spaces in the y direction. And we're moving there. So y used to equal -1. Now it equals -1 minus 3h. Because we started at -1 and we're moving in that minus 3h direction. And again, here we started at 3 and we're moving +1 in the h direction. So they foiled this to get this nice quadratic, of course. This they didn't change. They distributed it completely, which you have to appreciate. And then the 9s just ended up canceling out. I mean, if the 9s are going to cancel out, I'll be happy about that. But maybe the 9s will always cancel out, because that's the whole point, because we have the a here and the a here. Let's move on. Let's try -30. Let's just put the right answer in and see what they do. Okay, now let's see. Can we remember what we're doing? Don't quite think so. Oh, find the directional derivative. Exactly what we were doing before. Oh, this might be harder than we thought. For y e to the x, a is 1, -1, v is -1, comma 0. Maybe we should have taken a screenshot. But let's see. So -4e is f of a right there. -4e. But we need f of a plus h v hat. So instead of just 1, right, we're going to have 1 minus 1h, or just 1 minus h. But now instead of -1 for y, we're going to stay with -1, right? Because +0, we're not moving anywhere, even in the h direction of a minuscule infinitesimal mark. We're not even moving even that much. So that's going to be our x value, and then y is still just going to be -1. Let's erase just some of this. All this stuff we already know. -4e, we can remember that for f of a. But 1 minus h, -1, that's our x value and our y value for this function. So again, y, -1, so that's going to be -4. E to the 1 minus h. And then we had that minus -4e, so that'll be plus 4e. Minus a negative comes a plus. And now that's all going to be over h, if I remember correctly. This is interesting. We can factor out a 4e, for sure. Get negative... Oh, I don't know if we can factor out a 4e. We're making a mistake. E to the 1 minus h, e to the 1 divided by e to the h. Put a -4 on the outside. That e factors right out. We only factor the positive, so we're keeping that negative sign. -1 over e to the h plus 1. That's that for e. All over h. Oh, I just don't know. I just don't know. We can definitely have that be negative e to the -h. We can do that. Still just don't know. Let's put this in and see what it tells us. Okay, let's try that. See if we can learn anything. That's what we're here for, right? Trying to learn. 4e negative e to the negative h. That's gonna be this term. Negative e to the negative h plus 1. Now this is where we're not really supposed to have an h anywhere. Oh, but the h does go to 0. Remember the h goes to 0. I might have been forgetting that. E to the negative h. God, there has to be an h on the top that cancels out, right? It's usually how it works. I don't know. We know anything to the 0 is 1. This might be negative 1. Negative 1 plus 1 is 0. If we put if the top is 0 and the whole thing equals 0, I don't know what to say. Not quite. I knew it. Let's get rid of all this. So we knew that the negative version was 4e. We knew that. When a directional derivative is in the direction 1, 0 or 0, 1, it becomes a regular partial derivative. That does make sense. Are we kind of taking... My understanding is not too great. Maybe we'll watch a video. Might just have to. Because we just wanted to take the directional derivative with respect to x and make it negative, right? That's all we were doing. Plugging in these numbers. Respect to x, make it negative. Let me think. That would be 4e to the x, negative 4e to the x. Yeah. The x would be negative 1. The x would be 1, the y would be negative 1. Oh, I see. I think we might have to watch a video. I didn't want to do it, but we might just have to. I need a way to clear the screen, but I just don't know if I don't think I have that. Let's see, Khan Academy guy, what do you got to say?
Hello, everyone. Is to take a look at y is equal to 2. And if you're taking with respect to x, you think about just nudging a little bit in that x direction. And you see what the resulting nudge is in the output space. And the ratio between the size of that resulting nudge and the original one, the ratio between partial f and partial x, is the value that you want. And when you did it with respect to y, you were thinking about traveling in a different direction. Maybe you nudge it straight up, and you're wondering, okay, how does that influence the output? And the question here, with directional derivatives, what if you have some vector, v, I'll give a little vector hat on top stemming from the original point, and you're wondering, what does a nudge in that direction do to the function itself? And remember, with these original nudges in the x direction, nudges in the y, actually taking a step along that, but you'd be thinking of taking a step along where you take a negative 1 step by x, and then 2 of them up by y. So when we actually write this out, the notation, by the way, is you take that same nabla from the gradient, but then you put the vector down here. So this is the directional derivative in the direction of v. And there's a whole bunch of other notations too. I think there's like derivative of f with respect to that vector is one way people think about it. Some people just you end up calculating it. And if I was going to be more general, let's say we've got a vector w.
Is this it? Because for some reason it felt harder than this. But I knew that it was going to be way too hard when they gave me all the limit definitions. Everyone knows that you don't ever have to use the limit definitions. This is what I was expecting more. Okay, this we can do. You basically use this as a constant in front of its respective partial derivative. So negative 1, you would have negative 1, the partial derivative of x, if it was in your x spot. Here, if 2 is our constant in our y spot, you would have 2 and then our partial derivative for y, which is exactly what he says right here. So maybe I think we're ready for the quiz. We were trying the practices. We were babying ourselves around it. I think we're ready for the quiz. 36 minutes ago. We might not have time for too much. Honestly, before we take a breath here, I'm getting tired. I thought we were going to do this after every quiz, but, we might have to change our plans. Let's check out our math snacks this week. 105 by 2 on the snatch. Not too bad. See where we're at next week. Okay, quiz number 2. We're going to say resume, but we're starting over. Oh, we have one right? That doesn't sound right. I must have... Oh, it must have been just a normal partial. Okay, so this one... Oh, but I forget. I forget what to do with this. Oh, what a disaster. I remember this, though. But now it's just a partial with respect to the z. Something like that. Minus 2z would be our partial here. With just a constant of 1. Oh, man, this is where I'm not going to know what to do. Minus 2z. That's the big partial. That's all we got. Minus 2z. Maybe this is now we just plug in our z value, and let's see what we get. Is it just positive 2? Do we just get the partial derivative and then plug in these values for our variable values? Because if so, and z is negative 1, this answer would just be positive 2. I think I'm going to be onto something. What is the gradient of f of p drawn like this? What do we say? The negative gradient brought it down, so the positive gradient brings it up. This looks like up to me. Perfect. Find the gradient. All we do is we take the partial derivatives, first variable x, second variable y. Partial with respect to x, ooh, you guys aren't going to get tricked by this. A little bit of chain rule, right? All we do is bring the 2 to the front, not too bad. And then we subtract 1 from the 2, so it just becomes the normal function itself, right? So derivative with respect to x, we see this minus sign separating the functions. This function doesn't have an x, gets canceled out, it's just a 0. Now we look at this function. Minus 2 sine x, chain rule, derivative of sine, cosine. Minus 2 sine x, cosine x. Minus 2 sine x, cosine x. Now derivative with respect to y. Again, this function has no y, separated by a minus or plus sign, canceled out. All we do is look at this one, or becomes a 0 because it doesn't have the right variable. 2 cosine y, chain rule derivative of cosine, negative sine y. Negative 2 cosine y times sine y. And now you might see these are actually very similar. It's just the x is switched and the y is switched. Because while the 2 came from in front of the sine or the cosine, they're all multiplied together, so it doesn't actually do a big difference. And the minus is kind of surprising where it comes from, but it's only because it's right here, so the minus comes here automatically, and here it comes from the derivative. So let's check. Yes. I was nervous about that one, but we got it. So now this is where we can try our theory, right? We're going to take the partial derivative of x, y, and z, but we're not going to have to put any coefficients in them because these are all 1. And then whatever our values of, or wherever we see x, y, or z, we can plug in these values. So let's see if that works. First, let's rewrite this function with a z to the negative 1. Because I'm just not that smart, and when I see it on the bottom, I don't know what to do. I don't know what to do. I need to see that to the negative 1 so I can treat it just like an exponent. X, y, z to the negative 1. Perfect. Derivative with respect to x. X just goes away. We just get y, z to the negative 1. Derivative with respect to y. So let's write that. Y, z to the negative 1 plus our y derivative, x, z to the negative 1. Y just goes away. Now our z derivative, what do we get? xy negative z to the negative 2. Negative comes all the way to the front. Maybe we can undo this plus sign. We'll turn it into a minus sign. Perfect. Minus x, y, z to the negative 2. Now I think this is where we just plug in our values. Y is 2 times, 1 over 1 is still just going to be 1. So we'll just leave it as a 2. Plus x is negative 3. 1 over 1 is still just going to be 1. 2 minus 2 plus negative 3. We'll have a negative 1. Let's save that right now. X, negative 3. Y, 2. Z to the negative 2. That's going to be 1 over 1 squared. Still just going to be 1. It's all multiplied together, not going to do too much. Not going to do anything. Minus 3 times 2, negative 6. Minus negative 6 is a plus 6. Negative 1 plus 6. I'm thinking 5. This would get me a perfect on the quiz. I hope I'm right. That's what I'm talking about, guys. That's what I'm talking about. Before we start quiz number 3, let's check out our max barbell row. 135 by 6. I think the reps look pretty good. I think I might have had more, but we'll see where we're at next week. Okay, the only lift we have next is the deadlift, so let's see if we can finish in this episode. With how long quiz 2 took me, I'm not optimistic, but we'll see what we can do. Suppose we have a vector valued function g of t, scalar function f of xy. Let h of t equal f of g of t. Okay, we know g of 2 equals negative 4 comma 2. G prime of 2 is 1 comma 3. Okay. Delta f at 4 negative 2 equals 6 negative 2. Evaluate dh dt at t equals 2. I see. H of 2, f of g of 2. G of 2 is negative 4, 2. F of negative 4, 2 is 6 negative 2. Right? 6 negative 2. Oh, delta f at negative 4, 2 equals 6 negative 2. Ooh, I don't know what to do here. Negative 4 comma 2. We're looking for f of negative 4 comma 2. But we're looking for dh dt. Oh god, I just don't. Maybe we have to do some chain rule stuff here. H prime of t. If I'm thinking of a basic chain rule, I take the derivative of the outside function times the derivative of the inside function. That's what I'm thinking. That's how you do the chain rule normally, right? So we're looking at f prime of g of t times, it's fine, times g prime of t. I don't really need this set of parentheses, but it's not the end of the world. Again, t is 2 here. Let's put a bunch of 2's right here. G of 2, negative 4 comma 2, f prime of negative 4 comma 2. That's where you get the 6 negative 2. Now I'm assuming the chain rule, g prime of negative 2, we get 1 comma 3. I think you get 6 minus 6. 6 times 1 is 6. Negative 2 times 3 is negative 6. Add them together, you get 0. Maybe? Is that... If that's right, I'm going to be happy. I think it's called a dot product, but I don't actually know. I forget. Hopefully it comes up later and I need to learn it. Hopefully by the time of the end of each unit, I may go back and make sure I have a good understanding of everything, but first step, let's just see if we can get through the quizzes. H prime of t equals f of g of t. H of t equals f of g of t. H prime of t. We know we have to do the same chain rule, so it's going to be f prime g of t times g prime of t. And then I think it's time to do some directional derivatives or something. I'm sure we'll figure it out. F prime g of t, g prime of t. F prime t sine 3t 2 sine t. F prime, we're just going to go for it. 1, 3 cosine 3t, negative 2 cosine 2t. That's what I'm thinking. That is, ooh, f prime of g of t. Oh, I made a mistake. This is just what? This is just g prime of t. I just did g prime of t, didn't I? So that's actually this term right here. That's not this term. So let's try to save that. Maybe I'll try to write it a little bit smaller so I can erase everything else. Let's just write that. G prime of t equals 3 cosine 3t. And these are the partial derivatives. This is the partial x derivative. Ooh, or I don't even know. Well, maybe I'm right. We'll see what happens. I just took the derivative of each of these separately, but they were all derivative with respect to t, which is the only thing that kind of scares me. But I'm not too scared. Let's see what we can do. F prime g of t. That's what we're looking for now. F prime g of t. So the first thing that we want to do, let's write it out just to be a little bit clearer. F prime g of t. We want to plug in g of t into our f prime. So what's our x value? Our x value is t. What's our y value? Our y value is sine of 3t. Our z value is sine of 2t. So let's rewrite all of these x, y, and z values as the x, y, and z values that we're plugging in. And let's see what that does. Z, we have sine 2t times x squared, t squared, x is just equal to t, plus y cubed sine cubed of 3t, because y is just sine 3t, so it's just y cubed. And that's it. Z, x, y. That's the whole function. And now we take the derivative of this, the partial derivative, just the derivative. Ooh, I don't know. I don't know. Luckily, this isn't. I'm not close to getting it perfect on the quiz. So nothing too bad's going to happen. Because this is just f of g of t. All I did was plug in g of t into f, so I haven't even taken a derivative yet. And now the only problem is that maybe, oh, I know what I made a mistake on. Oh, classic. I need to take the partial derivative and then plug in my values like I've done before. Oh, what a silly mistake. Partial derivative, first we're going to get 2xz, comma, partial derivative of y, we're just going to get 3y squared, obviously. Again, basic stuff. X derivative, don't even use this term, doesn't have an x. Y derivative, don't even use this term, doesn't have a y. Z derivative, again, just going to be this term. Z is going to get rid of, just going to have an x squared. Now this is starting to make a little more sense, isn't it? Because now we have three numbers here that we can do our dot multiplication like we thought, what we think might be dot multiplication. 2xz, 2t, sine 2t. Perfect. 3y squared, 3 sine squared 3t. Y is just sine 3t, y squared sine squared 3t. Comma, t squared, x squared, t squared. We have our y is 3t, our z is 2t. This is looking okay. X times x, 2t sine 2t like that. Again, we can have our t in our answer because we have a t here. We don't have a value to plug in for t. We just have the t, so we're going to want that to stay. Now plus this times this. Oh no. 9 cosine 3t sine 3t. That's what I'm looking at. 9 cosine 3t sine 3t. Plus our last term, t squared, negative 2 sine 2t. Negative, maybe, can we turn that into a subtraction sign again with some undo? We can. Minus 2t squared sine 2t. Minus 2t squared sine 2t. If we get this right, we'll try to finish the quiz. If we get this wrong, I might show you my max deadlift and move on. I think we made some good progress today, but this might be right. Let's see what we got. Do we need to factor anything out? We cannot. We can't factor out a sine 2t. We can't factor out abnormal t. It's only these two. Let's go for it. These two are very similar. It's just a t that's different, but we can't actually factor it all the way out of here. So we could factor, we could separate, we could put these two next to each other, separate this one, factor out the 2t sine 2t. We would get 1 plus t, but I don't think it's that important. I think it'll accept it either way. Oh, but we definitely need to definitely need to keep it on the screen, or I'm going to forget it. Okay. I believe it. Let's go for it. 2t sine 2t plus 9 cosine 3t sine 3t minus 2t squared sine 2t squared sine 2t. Now let's hide it, see if it looks correct. 2t squared sine 2t. That was the only thing I was concerned about. I think we pressed check, guys. No! What did we do wrong? Guys, I think we get help on this question. I'll show you my max deadlift and we'll see. We'll move on. What did I say? 2t squared cosine 2t. Did I make a mistake in a derivative? Oh, no. Guys, I think we have the method right. I think, a silly mistake. Where does it look like I must have made a mistake? It looks like this should be a cosine or something. Oh no, I can't see anything. I can't see what my work was supposed to mean. But it was all completely right except this was a sine instead of a cosine. And where did that come from? That came from the g prime. No! No, I even made it a negative because it's negative. The derivative of sine is cosine. Why did I make it negative? Did I think this was a cosine? Did I read this as cosine 2t when I took the derivative? Oh, it's a disaster, guys, but we'll be back at it next week. We'll make some more progress. We'll end it off with our max deadlift. See you guys next time.